For those of you who are just barely getting back in the swing of things from the holidays, I hope those went well. And I hope this seminar isn't too soon in the week. We're very grateful to our speaker today, Pieter, who is going to be talking to us about the San Andreas fault, well, the Salton Trough segment of that. We're grateful that he's willing to give us his time so early in the year. It's my pleasure to introduce him. Pieter studied physics and geology in South Africa before coming to the United States. He was at the Nelson Mandela Metropolitan University and then the University of Witwatersrand. He also spent some time at the Dublin Institute for Advanced Studies, receiving a master's in 2012. Then he came to the United States and did his PhD at USC, studying the San Andreas fault system. And then you might remember he was a Green Scholar here quite recently, actually, from 2018 to 2020. And right after that became an assistant professor at Oregon State University. He does both MT and seismic methods. So he's sort of a diverse guy with a lot of different tools in his toolkit. And yeah, so without further ado, it's my pleasure to introduce him. And Pieter, the floor is yours.
Thanks so much, Dan, and hello, everyone. It's quite special to me because as Dan said, I was at IGPP not too long ago. And you know, my in-person time was cut there a bit short because of the pandemic, but so goes life. And this is also nice because I'll presenting on only stuff that I either started and finished at my time at IGPP or stuff that I started and still in the works to be finished in the near future. So, you know, Dan read the title. It's going to be focused very much on Southern California, Northern Bar, California. And in the title, well, is the term multi-scale. And so just to give you an idea what multi-scale means, or what I mean by that, is that on the left, we are going from, let me just, whoopsie. So I'll just use my cursor. So on the left, what we have at the scale, it's the 100-kilometer or so scale. And on the rightmost plot, what we have is all the way down to 100, 200 meter length scale of focus. And yeah, I'll be looking at various different data sets. I can't get through all of it today, but the focus, as Dan said, is mostly seismics and then electromagnetics. And I'll be focusing on various fault systems and the plate boundary in this area. So kind of my mission statement when I started the postdoc at IGPP was to do exactly this, was to focus on the nature, structure, and strain of the southernmost San Andreas fault system and using a variety of tools. Geology, seismology, EM, geodesy, neither of these need an introduction for the crowd today. But then, you know, as we evolve in this field, we start to use new technology. I mean, using drones for LiDAR surveys, using nodal deployments for dense seismic networks. And then as soon as we use these tools, we have to start looking a bit more at big computing and data. So I try and cover these topics in my work. But once again, I can't do all of that today. I'll only focus on some of it and some highlights of the work. So why do I care? Why do I even care about fault zones and plate boundaries, these anomalous features that form part of a tectonic framework? Well, in the first case, a fault zone is critical, and it's a big driver in the way an earthquake rupture behaves in real time. So on the left over here, you've got space, you've got time. This is simulation of slip on an earthquake fault or a rupture. And how you interpret these broadly smeared orange and red colors is simply that this entire fault plane is slipping almost instantaneously, and a large part of the fault is in contact and taking part in this earthquake rupture. As soon as you add a little bit more damaged material or deformed material right around the fault zone, what happens is that the physics changes. And in this case, these vein-like features that you see in this plot simply tell you that we've gone from a crack-like rupture to a pulse-like rupture. So the rupture itself is now much more confined in space and time. And the gradients or the slopes in these vein-like features tell you that we are also now encountering some super shear rupture behavior, just with the inclusion of a fault zone or multiple ruptures causing damage along a fault. And you don't even need that. You don't even need damaged material. You can just smack together two different blocks of very different material. And then one slip occurs on a fault like that, and we call that type of fault a bimaterial fault. What happens is that there's a dynamic reduction of normal stress more so on the compliance side of this block. And what you then get is, once again, a bit more pulse-like rupture behavior. And there is also now a preferred rupture propagation direction at subshear speeds in this case. And that would be in the direction of the compliant block. So this blue block at the top. So that's how the earthquake works. So the earthquake rupture works as it happens. But of course, these type complexities also influence what the wave field behaves like as it propagates away from the source or the fault where the earthquake occurred. Over here, you just add a little bit of irregularity to a fault plane, and what you get is a modulation of the wave field away from that fault plane, especially in the high frequency side of the spectrum. So we get these high frequency impulsive signals that are coming out of the irregular fault, and those can obviously be quite a bit damaging, both near the source and in the far field. And secondly, if you add a bit of plastic material, deformed material, right along where a fault occurs, in this case, the simulation was done for the San Andreas, the Mojave, and the San Bernardino Mountains. What happens here is that plastic material essentially sucks up a bit of that seismic energy that's being emitted away from the fault. And then in the far field, what you have is a reduction in the amount of ground motion that's experienced. So this top plot, we have no plastic or deformed material. And so you experience a level of ground shaking in the LA basin. In the bottom case, you add a bit of that plastic material, and then there's quite a dramatic reduction in the amount of ground shaking experience. So fault zones are important because they influence the physics, but they influence also how the seismic wave field actually behaves as it's being moved away from the source. So here's my rough outline. I'll be focusing firstly on the larger scale features, and I'll focus in very specifically on the San Jacinto Fault and the southernmost San Andreas Fault. These fault systems in the area in general probably need no introduction for everyone on this call. So starting with the plate boundaries area, and it's by all means complex, and it's complex because what we have here is the confluence of all three plate boundary types. We've got the famous San Andreas fault system, this or at least the San Andreas fault proper. You've got this red line, it's a transform plate boundary. Then you have incipient rifting starting towards the south in the Gulf of California. So now we're going from a transform to a divergent plate boundary. And a bit more obscure here, but these gray colors in the map are elevated regions in Southern California, Northern Baja California. And these are obviously the Peninsular Ranges, and they are remnants of past subduction in this area, subduction of the Farallon plate, that is. So we've got different timescales, different plate boundary types, all interacting within this small zone. And so we can expect a bit of complexity, and that's exactly what I'm trying to tease out here. And so just starting with some fundamental tomography techniques, seismic tomography that is, I'm going to apply a triple difference tomography tool to this region. That simply means that in addition to the traditional travel times that we have from source to receiver, resolving structure along the ray path, connecting the source and receiver, we can now start combining data from station pairs and from event pairs at depth. And what you essentially get when you do that is that you firstly have a much larger data set that you have to work with. But secondly, you get more of a holistic image of the subsurface from the near surface all the way down to the base of the seismogenic zone. So you get a better and bigger picture. So just, I'm not going to repeat this, but a brief introduction of just the station coverage, the seismic events we used. And as you can see, it spans both Southern California and Northern Baja California. The Northern Baja data comes from SSAF, and these in Southern California come from the Southern California Seismic Network and also from the ANZA network, which Frank Vernon and his team have been working on so thoroughly and diligently for much more than a decade. And so, you know, a ton of data, and then once you start combining these data in pairs, it starts to increase dramatically. And so we have, I think, about 4.5 million data points that get put into this conversion. And it runs, and I'll just show you some slices. I can't spend too much time on this. But essentially, what we expect in a region where we have some rifting is indicated by this image on the left. So right at the surface, you might have a bit of a lower lying crust that gets filled in with sediment. And so you would expect lower than average seismic velocities right over the region where you have a bit of rifting. And as you go deeper and deeper and deeper, what you expect to see is you encounter those higher velocities of the uppermost mantle at a much shallower depth than what you would do on either side of where you have rifting. But in short, this is not what we see in this region. I'm just showing you at 8 kilometers depth where we have some geothermal activity, some volcanic activity in this area, indicated by these circles and triangles. At 8 kilometers depth, we have pretty much average VP speeds in this area instead of very low. You can see surrounding it, you've got these low velocities. As you go deeper and deeper, deeper, once again, you don't encounter those high uppermost mantle velocities first in the regions where we have this geothermal activity. So simply, we probably have a bit of serpentinization going on at uppermost mantle depths beneath these volcanic and geothermal areas. And that is lowering the seismic velocities at those depths a little bit. And near the surface, these high temperatures are probably baking and metamorphosing the sediments a bit faster than everything surrounding it. And that's why you have a bit of elevation in the P-wave velocity speeds at those depths. Another interesting feature that came out of this model was the super prominent shear wave velocity feature that strikes quite parallel to the 2010 El Mayor Kukupar event. And it starts showing at about 40 kilometers depth, and then extends all the way down to the base of this model space, which is about 25 kilometers depth. And as you can see, an elongated feature, definitely a corridor or a region of fluids, deformation, and damage that has been formed in some way by the interaction of rifting and transform plate-bound behavior in this area. And just note, it's not only the El Mayor Kukupar event that occurred nearby this feature in the mid to lower crust, but there were several magnitude 5, 6, and larger events that occurred within 15 kilometers of the zone. So this is without question a pretty high activity corridor within this tectonic framework. And if you look at the VPS structures a bit more carefully, I'm not showing that here, but it really seems that whatever is causing this feature is kind of leaking into the Salton Sea area or the Coachella Valley area as you go to mid and upper crustal depths. But we can chat a bit more about that if people are interested afterwards. And so simply, I'm just thinking, we had these detachment faults. You had an accommodation zone between the western dipping section of this and the eastern dipping section of this. And then you have these transfer faults being formed in that accommodation zone. So, maybe these transfer faults they played quite a big role in the formation of this high activity corridor that's extending all the way from the Pieter Fault all the way into the southern San Jacinto Fault in Southern California. But yeah, that's just kind of one idea. But without question, this is a prominent geophysical feature in this area that I think deserves a little bit more exploration. Okay, so I'll move on. I know that was quick, but let me move on to a very different scale and a very different topic. And so the focus will now be the San Jacinto Fault, which is the one I just mentioned as part of that high activity corridor in the previous topic. And this is a highly active fault system, not only in everyday seismicity, but also in the large scale earthquake ruptures it causes over time. The last two occurring around 1800 and 1920, I think it is, magnitude 7 and greater events. But you can see, in comparing it to the other faults in this area, these little colored dots are everyday seismic events, and you can see it's a very active fault system. So let's see if we can harness that power. Let's see if we can do something interesting with it. And so the topic now becomes fault zone head waves, which is a very specific seismic phase that we can use to inform fault properties at depth at very high resolution. Now, a fault zone head wave is very similar in the physics compared to refraction seismology or head waves that we find in exploration seismology, but you can see the geometry is a little different. So in the exploration case, you've got a source of the surface. The energy propagates down, it refracts at a critical angle with that slow, fast interface. This might be sediment to basement rock. And that critically refracts back and emits energy continuously to your sensors near the surface. And at some critical distance, you obviously start to see the head wave arriving first at a station. Now, once again, the geometry is very different for a vertical or near vertical fault. And we can control somewhat, sometimes, where we put the stations at the surface. We can definitely not control where the earthquakes occur. But the power here is that the earthquakes occur on both sides of this interface, not only on top of the slow side or on the slow side of the fault. So we can harness that, and we can harness that in the following way. I mean, from any event near the interface on the slow side, we will have some direct body wave arrival, and then we would have this critically refracted fault zone head wave that propagates just on the far side and emits energy continuously towards the stations at the surface atop the slow block. Now, the event right on this interface is going to have a higher difference in arrival time between the fault zone head wave and the direct wave compared to an event that's on the slow side but farther away from the interface. That's just like simple physics if you look at how the ray paths go. So that's quite powerful, right? Because now we have a tool here. If we analyze gradients within this differential time field across our interface, and you find the event with the maximum differential time, you are probably right on this biomaterial interface at depth. So you can just imagine if you have this cluster of seismicity and it's not delineating very well for you where the fault or the fault proper is, but the fault is biomaterial, you have a tool here to pinpoint within that cluster where exactly that biomaterial fault locates. So I'll try to do just that. And just a spoiler alert, this is still in progress, but it's exciting stuff. And so I can really go ahead, and we can really go ahead and use some of this magical data that Frank and his team have been installing, maintaining for more than a decade in this area, these seismic arrays and networks that cross the San Jacinto Fault across different sections. And I'm just showing you one example here of the type of data coverage we have. We have month-long data for a 2D vertical component only nodal array. These red dots are 3-component nodes in the same area. And then we have more than 10 years worth of data for a shorter aperture, 3-component broadband accelerometer network in this area. So we have all these data sets that I'm going to use in the way that I'll describe in the following slide. So what I simply do is I just start with a 2D array, and I look at what we have, and then I break it down to smaller and smaller scales. And so on the left here, here's an example of what a head wave and a direct wave looks like. So this very first arrival, this low amplitude emergent type phase is your head wave. And then later on, you have this emergent phase this impulsive phase arriving with a slightly different move out across the array. And that makes sense because they're coming in at different angles. And so this is what it looks like across that 2D array. You can see the fault zone head wave has a characteristic move out across the array. It's pretty similar. These are two different events. Apologies, I sort of mentioned that. But so this is for the one event. You can see the way the fault zone head wave move outs across the array is pretty similar for these two events. Between the two direct wave, it's also pretty similar. But if you look at the difference between the two, the shape in the move out across the array is the same, but the amount is very different. You can see for this bottom event, generally speaking, those differential times are elevated by a few fractions of a second. So that just simply tells us that this event that generated this differential time for us is an event that's either right on the fault, or it's on the fault or near the fault and farther away from our recording station compared to the event shown in the top panel. Okay, so that's the visual idea of what's going on here. So I do that. So I identify these phases. I identify template events for these phases using the dense arrays first. I point out where they are, and then I go down in a cascading fashion to smaller and smaller aperture arrays. And so I can start seeing them in the 3-component P network, the 3-component S network, and then finally in that more than 10-year long recording window, very short aperture accelerometer network they have in the area. So this is just we're moving from large aperture, high quality, but low event type recordings, all the way down to short aperture arrays, but data that span a decade and more. So we can look at many, many more events once we've done this quantification for these shorter aperture arrays. So this is kind of what that differential field looks like. Just looking at events that have good quality results in this case. And as you can see, there are almost peaks and troughs within this differential time field. And so the thing that I'm busy with right now is quantifying correctly where the peaks and troughs within this differential time field is, and then pinpointing where the fault is. And once I know where the fault is, the biomaterial fault is, I can pinpoint more clearly what the velocity contrast along that patch of the fault is. And just note, I mean, these kind of show you highs and lows within this field. But remember, this just represents, represents patches of the biomaterial fault at depth, but it also implies there's continuity between these fault patches at depth all the way to our recording station at the surface. If there wasn't continuity, we wouldn't be seeing faults and head waves in the first place. So we require continuity, and from that continuity, we can infer various properties of the fault at depth. So this is the P wave results for sagebrush. This is what that S wave result looks like, just for a smaller area, because the data are a bit more noisy, so you can't do it for the entire seismic data set. And you can see there's some correlation between the peaks and the troughs, but some differences also, which is quite interesting, I think. And so, as I said, at the moment, I'm trying to tease out what exactly this means and trying to figure out what this geometry is going to be like at depth. What we know from various other studies that suggest we do have some gentle northeast dipping of the San Jacinto Fault zone proper as we go to greater and greater depths. And just comparing two different arrays, this is for the sagebrush, that's for the Ramona array, which is 10 kilometers towards the northwest, also along the San Jacinto Fault. Here we also see some of these phases, but you can see the peaks and the trough within this differential time field is a little bit different. It's not exactly the same, which is quite interesting. And I thought at first this might reveal some anisotropic properties right on the fault plane at depth that's being recorded by these two different antennas that are aiming or viewing these event clusters from two very different angles. But it might just come down to the complex geometry at depth that is causing these differences. But stay tuned. I'm busy working on this right now, and I'll have some more clarity on that topic pretty soon. Okay, moving on. So we are done with the San Jacinto for now, and now I'll move to the enigmatic Coachella Valley segment of the Southern San Andreas Fault. And as many of you know on this call, it's enigmatic because it's pretty quiet. It's pretty quiet, seismically speaking, on an everyday timescale, but we know it can and it will produce major earthquake ruptures in future. And so it's important to study. It's important to quantify a bit better. So I just thought when I started my time at IGPP and I had a chat with Steve Constable and Jared Peacock at the time, I was like, listen, yeah, I mean, we've got this great tool called MT. It's a non-seismic tool. This is a seismic target that's aseismic. So we don't have those everyday seismic events to help us figure out exactly what's happening at depth along this fault. So we just need maybe a different perspective. And that's what we had hoped the MT tool would give us. And for those of you not familiar with what MT is, it's an electromagnetic type geophysical tool. What you go out to the field, you have electrodes, you've got magnetometers, you lay them out in an orthogonal manner, as I show on the right over here, and you record for a few minutes, a few hours, even up to a day at a site, and then you move the station along a profile until you're done. You know, compared to some seismic tools, this really goes fast. We did this entire 30 kilometer or so profile in 6 days, and we were done. And we had a data set, and the analysis could begin. And so just to briefly lay out what this model kind of looks like, you don't have to be a specialist in this field to get the general trends in this data. what I'm showing you are tippers and phase tensor results. So what you're simply looking for is that the alignment of these ellipses and the direction of the arrows, they tell you the dimensionality of the structure and also where you might be encountering some prominent conductors along this fault zone. So you can clearly see, if you just focus in on these arrows for now, so you can see on the southwest side, all these arrows are pointing towards somewhere beneath the fault zone. Same for these tipper arrows up to a certain period. For the northeast side, they are already indicating that we have some very conductive material right beneath this fault zone. And just to mention, sorry, so low period at the top, longer periods at the bottom. So you're increasing in depth as you go down and also increasing in the scale that you're able to resolve. And you could also note that these ellipses are kind of horizontally oriented on this side. And as soon as you cross this arrow, there's a clear rotation and you have more and more vertical orientations of these phase tensor ellipses. That immediately tells you that you have now crossed some large electrical conductivity contrast, more or less at the location of this arrow. So that's kind of the initial sense we got out of the data. But of course, then we go ahead and we invert this data set and we get a pretty looking model like this. And so I'll explain all of this in a second, but just the general overview, these magenta dots are the local earthquake seismicity in this region. All these very deep blues are resistors, so rocks that do not conduct electricity very well, very dry, very cold, especially at crustal depths. These red, yellow, orange structures are conductors. So these are deformed, damaged, depending on the depth, fluid-rich structures that are also conductive in nature, and that's why they show up in the way they do. And so in general, what we see, we have three conductors that are very well resolved. C1, like right at the surface, we've got C2 over here and C3 over here, and then we've got this broad region that's pretty resistive. So you can already see there is some geometry related to C1 near the surface. So we can already say that the southern San Andreas fault zone, at least at this location, within the upper crust, definitely seem that the fault zone as a whole definitely seems like it is dipping quite steeply towards the northeast. But now, of course, now the question becomes what happens at greater depth. And as I noted in that previous slide, what we have, which is a very robust and very, very key feature in this model, is this contrast between conductive or something being averagely conductive to something very resistive that extends vertically, pretty vertically down from the location of the arrow all the way down to when we start losing resolution in this model space. So to me, what we kind of came up over here, I'm sorry, I just should have skipped over. So yeah, just to mention again, those are the two features that are very, very well resolved. And then as you go to greater depth, these two deeper conductors, I'm pretty excited about this, but you know, as soon as we cross the brittle-ductile transition in this area, that is when these two conductors start showing up. And in fact, lower crustal conductors in highly active tectonic regions is seen quite ubiquitously in MT models and electromagnetic models. And people normally say that that probably relates to some minute amounts of saline fluid that is interconnected over very, very large distances. It's one possible cause of these type conductors, which to me is quite exciting because these might be essentially fault routes that are manifesting at ductile crustal depths beneath the San Andreas fault system. And so what exactly makes sense here? And there are two hypotheses that we came up with in this paper, which is in review right now. I mean, it's quite clear that we must have some steep northeast dip in the upper crust. But deeper down, you've got two scenarios. So either the San Andreas fault proper or the fault zone becomes more vertical at greater depth, and it is this barrier for fluid migration towards the northeast, or it continues from where C1 is, and it manifests as C3 in the ductile crust, and it passes through this region that is super resistive, which means that this fault zone at mid-crustal depth is very dry, or the cracks or the features that exist along it is way, way, way below the resolution capabilities of this tool. That's what we have for now. I mean, what we really need is more data. More data along this fault system, and more empty data all along the Salton Trough. And that's exactly what Steve and I and collaborators have proposed. And this is under review by the NSF right now. And so we'll see what they say. We're supposed to hear back pretty soon. But my hope is to kind of go out and see how these features continue along the San Andreas fault system, and how it actually continues all the way across this anomalous Salton Trough area that many of you have studied as part of the Salton Seismic Imaging Project, for example, which is shown in the bottom left plot over here. So we're mimicking in a way what has been done before in this area, but just focusing much more on the electromagnetic component of analysis. So we'll hear back. We can only hope that it's good news, and we can go out and collect some more of this type of data and make some more sense of the area. And just the final topic here that I'll speak about is something spearheaded by Yuri Fialko and then Frank again at IGPP. This is now a seismic nodal array that we installed in early 2020, in March of 2020, just before the pandemic disrupted everything. And there's a layout of what the 320 nodes look like at the site. And it's exactly the same site where that empty array was installed, but the aperture of this dense array is about 4 kilometers, whereas for the empty profile was 30 kilometers. And just for those of you interested, these are the details that came out of this experiment. In fact, we installed in the beginning of March. We were supposed to take these out in the beginning of April, but as all of you know, things were shut down completely, and we had a flash flood event. And so the retrieval of this nodal array, which is normally the easier part, was actually much, much harder. But thanks to Frank and Yuri and many others, they got them out of the ground. In the end, we only lost 16 nodes, which comparatively speaking is a low number for the conditions that were prevalent at the time. 8 of the nodes were just washed away by the flash flood event, but then later found. And so that data was useful, at least for a part of the time window. And then, yeah, we're just looking at the data still. Many groups are looking at different facets of the data set, and I'll just show you what I've kind of focused on, which is just the basic features of the fault zone that these data reveal. And we can do that. I'll show you a teleseismic P wave field in a second. We can look at the arrival times of these type of events. We can look at refractions, reflections, transmissions of these phases across the different fault zone. And we can actually tell a lot about what the subsurface structure is like, just by looking at some of those basic features. In this case, you can really clearly see that this wave field is convolving very differently with the Banning fault strand in this area compared to the Mission Creek fault. So the crustal structure is very different near those two fault zones. And you can see there's a region here between the two arrays or two fault strands where that difference manifests quite clearly. Those are lower frequencies. They tell us about general larger scale features. We can look at high frequency energy too. And for that, we look at some local P wave arrivals from local earthquakes. And I can see even finer details. You can now see that there's a region here a little bit southwest of where the Banning is mapped, where we have some rapid changes in wave field properties. So we know that there's an interface here that is sharpened density and seismic velocity contrasts that's really creating this modulation of the wave field in many interesting ways, and tell us something about the subsurface. So just briefly summarizing the teleseismic events, as I mentioned, you have this clear change in wave field properties at a location in between the Mission Creek and Banning fault strands. I'll tell you what I think that is in a second. And then for the more local arrivals, we can also look at the arrival times, P on the left, S on the right. We can look at what those look like across the array. That's the top plot at the bottom, at the top of here. So what is quite clear is that generally on the southwest side, which is this bottom side of the plot, material is on large scale and small scale is much slower compared to material on the northeast, which is not surprising because you've got the Coachella Valley sediments on the southwest side, and that progressively turns into the little San Bernardino Mountains, which are crystalline hard rock basement in the northeast. So the P variations are smoother. For the S arrival variations, you can see there's an extra delay for the S wave field just northeast of the Banning, just southwest of the Banning Fault, and just slightly northeast of the Mission Creek Fault. So we know there's a little bit of fault damage in this area, and it manifests almost in an asymmetric sense across both these fault strands. Even if you just look at the ambient noise level, what I did here is simply just take a median value of the vertical component ground motions for every day for that 30-month long window, all across this linear profile. And you can see on average of a broad frequency range, you have higher amounts of ambient noise ground motion over this entire recording window, which again is not too surprising because this is where we have those Coachella Valley sediments. And as we know, sediments are normally associated with some sort of amplified ground motion. And what's really exciting and what's still coming out of this project is that, I said before, this fault system is pretty aseismic on an everyday time scale. But what we do have are seismic events on either side of it. So the San Jacinto is very active. The Eastern California shear zone is very seismically active. So now we have these sources of energy that's not right beneath the fault, but is coming at it from some angle from the side. So now we can start looking at reflections bouncing off the major fault interfaces in this area. And on the left, I'm showing you a reflection that's coming off the Banning Fault. So this is for an event in the Eastern California shear zone, actually. And some of my colleagues have gone ahead and developed a reverse time migration tool that collapses these reflected signals back onto the direct arrivals on the other side of either of these fault interfaces. And the location at depth where these signals collapse onto each other show you pretty much where the main fault interface is, at least in the uppermost few kilometers. So we can only get down to about 2 to 3 kilometers with this tool. At that point, we start losing resolution. And as you can see, once again, I mean, it's quite consistent. Even with this very different data set, we once again see this very vertical to steeply northeast dipping fault interfaces associated with the San Andreas fault zone at this specific site. But of course, many of you at IGPP have done work along other sections of the same fault, and you've shown similar features. But once again, I mean, what's happening deeper is still kind of enigmatic, and this is something we'll continue to work on and continue to figure out, and hopefully we'll have some clear answers about that in the near future. So I know that was a lot, and I've left enough time, I think, for discussion. Hopefully there are some questions, but just to briefly highlight what I've gone through here is that this rifting in the Salton Trough combined with the transform behavior just creates a massively complex system. And it might have also helped initiate this high activity corridor that's associated with that low shear velocity anomaly and high VPVS anomaly that's striking relatively parallel to where the Almaty or Kukupal rupture occurred in 2010. And then for the San Jacinto, I mean, I need to tease out these data a bit more, but it's quite clear that geometry is going to be complex at depth. It's not going to be a simple planar structure, vertical, going all the way down. It's definitely bimaterial in nature. Otherwise, we wouldn't be seeing the type of signals I spoke about in the talk. And that contrast also seems like it's variable along the length of the fault. It is not a constant velocity contrast solidly or across this complex fault system. It definitely changes, which is not surprising given all the other complexities. And both the empty results and that dense nodal array I showed most certainly tells us that this fault system in the upper crust is steeply northeast dipping, deeper down, the empty results suggest two scenarios. I'm leaning more towards the fault zone is near vertical. It evolves into a more vertical structure at greater depth, but I know other data sets show something different. But what we need in this case, I think, is to cover the area a bit more using empty, but then also using some of the other very neat geophysical tools we have in our arsenal to figure out how some of those anomalies kind of extend along the fault system. And yeah, and maybe even if those deep crustal conductors are what I hope they are, they might suggest that we have not just one discrete fault route in this area, but maybe more than one that relates to some of the secondary faults towards the northeast of where the San Andreas fault is mapped at the surface. And I think that's also another cool topic to explore and to discuss more. And of course, I'm only the face here of all of this work. I have many collaborators and many contributors who have helped me with these projects and helped me generate these results. And these collaborators are ongoing. And yeah, I'm always on the lookout for more people to work with and more exciting projects to work with, and always on the lookout for more students also. And I think I should keep quiet for now and let people ask questions if there are any questions, because I know I covered a lot of ground, and hopefully there are some questions to be answered or asked about all of these topics. But thank you so much for your time. I really appreciate it. I know it's early in the year, but that's all I have.
Thanks, Peter. That was amazing. Thank you for your breadth of research. Does anyone have any questions that they would like to ask? I know I have a few, but I'll hold on to them and let other people go first. Patrick Dobson, do you want to go first?
Sure. Very interesting talk. I was just curious if you could say anything about the Brawley seismic zone, and if you see that as sort of like an accommodation zone for stepping over between the San Andreas, Imperial, and San Jacinto faults.
Yeah, thanks, Patrick. Again, a good question. So firstly, the Brawley seismic zone, the tool that I use, that doesn't only reveal seismic velocities first, but it also relocates some of the seismicity. So there's no question that the Brawley seismic zone is quite a shallow seismic zone. That manifests in that model as well. But that sits smack bang in the middle of where we see higher than expected P-wave velocities near the surface, and where we also see lower than expected P-wave velocities at greater depth. But you are right. So that low shear wave velocity feature, if you look at the VPVS model, which is in the sort of the teaser slide that Dan shared per email, if you look, it almost seems like that high VPVS anomaly extends all along the Almayokukupa rupture, and then it like feeds into the Salton Trough right beneath where the Brawley seismic zone is. So I think those cross-cutting faults and seismicities that the Brawley seismic zone forms part of, this definitely links up in some way or form with that anomaly that we see crossing the border into Mexico, and into that geothermal area near Terra Prieto. Yeah, I hope that answers the question, but yeah, it's consistent so far.
Thanks.
Thank you.
Thank you, Dan, and thank you, Peter. The talk was awesome, and I have some question about the VPVS ratio on the I think it was San Jacinto fault, which you showed at the beginning, and yeah, can you elaborate on that?
So is it so I think my
yes, the Salton Trough one, yes.
So is
where
this slide?
Yes, I think that's where the Almayokukupa earthquake happened.
Yeah. So the higher than average VP structure here, and in fact, yeah, if you're talking about VPVS, I don't think I've got a VPS plot over here, but that's once again in that picture that Dan shared. So for very granitic material, so granite is one of the rock types that is super low in VPVS, right? I think it's about 1.5 if you look at laboratory samples. So what we're seeing over here in the Peninsular Ranges, especially the eastern Peninsular Ranges, this is all granite. This is pretty much a solid chunk of granite. And so what we see is high VPVS values, but then, low VPVS values, but then compared to the VS isn't as low as the VP. So we actually see this large chunk of rock that is lower than average in terms of VPVS. And in fact, some of my previous work has shown that even in the fault zones where we expect there to be an elevated sense of VPVS, when you look at the San Jacinto at mid-crustal depths, at least, there we see even a greater decrease in VPVS right along the fault. We don't even see an elevation in the faults that cut through the Peninsular Ranges, which I think is peculiar, but very interesting. That's not always the case. I mean, I'm showing you an example here of a different fault, which is very active, that high activity corridor. And there we most definitely have these elevated VPVS features that we expect along an active fault system. But yeah, all that blues that you saw in the image that Dan shared per email, that's just the Peninsular Ranges. It's a solid chunk of granite. And it's just generally causing overall decreases in VPVS throughout the model space.
So in other words, you generally see lower VPVS ratio in fault zones.
Well, in that fault zone, in the San Jacinto fault zone, in parts of the San Jacinto fault zone that cut through the Peninsular Ranges, there is a decrease in VPVS. And I think some of Pieter Scherer's work a few years ago, where they looked at properties of the seismicity or how the travel times pair up.
Right. Yeah, I'm actually working on that on that method right now. That's why I'm interested.
Yeah, and it shows exactly the same for large troughs of seismicity, and I think this is consistent with that once again. But once again, it's not always the case. But I can definitely say for some of these major faults that cut through the Peninsular Ranges, they are even lower than the host rock itself, which is kind of unexpected, right? But
right. I think that's also what I'm finding in some oceanic faults. That's pretty surprising, I would say. Mm-hmm.
Yeah, and I think, just to compare it back to Pieter's work again, I think I made the same conclusion. It comes down to the crack geometry, because what I did see is if you have more metamorphic material, the cracks are going to be elongated and they are going to be very different geometry compared to cracks that might form in granite, because there's a very different crystal structure. So I think it might very well come down to the crack geometry.
Yeah, right. It's very interesting.
Yeah.
All right. Thank you so much.
Thanks, man.
Yuri.
Yes. Hi, Peter.
Hey,
thanks
Yuri.
for the talk. Very interesting results. I have two questions, one about the headwaves and another about the EM data. So in case of headwaves, I understand how they work if you have a nice, clean material interface. I'm wondering what happens in the presence of a damage zone. So for example, we have reasons to expect that San Jacinto in particular would have a pretty large damage zone. And in this case, you have a low velocity material and then perhaps higher velocity material on either side. There may be still a contrast between the two sides, right? So one is still higher velocity than the other, but really what is an interface in this case, and what does one expect in terms of the headwaves? And has anyone even done the forward calculations to see what happens there?
Yeah, thanks, Yuri. I'll answer that first, and then we can move on to the empty results. Yeah, good question. And remember, I'm also just showing you ray-based solutions or ray-based sort of models and toy models here. But these are finite frequency waves themselves. And I think Amir Alam and Yehuda, they did do some synthetic tests with finite frequency waves that showed that even the head wave has a finite region that it's sensitive to. So it is a wave that's mostly, or a signal that's mostly sensitive to the interface itself, and it's more confined to that interface than a body wave is. But it also is a finite frequency wave. So even if there's a damage zone, it might still see that damage zone as an interface if it's confined enough. And I think, I did a back of the envelope calculation once, and I think for a wave of like 10 hertz, given the velocities we expect, I think if the damage zone is tens of meters wide, the wave is going to see that as a sharp interface because it is a finite frequency wave. And so, the question between whether it's finite or not is a good question. And I think about that too. And in fact, some of the synthetic tests I'm doing to figure out exactly what I'm getting in this data set includes a damage zone in them. So I want to see what these head wave arrivals are doing when we do include a damage zone, because you are right. Firstly, the contrast and the location that we might estimate in a case like that might be biased in some way. You might not be indicating where the fault proper, the slip surface is. And secondly, the velocity contrast that you estimate might also be biased in a certain way. So yes, there will be biases. I agree with you. And that's where I'm really taking my time with this topic and doing as many synthetic tests as I can, because I'm really interested too what happens when we start adding damage. But you are right, at the San Jacinto, as you go deeper and deeper down, we do seem to still have regions of damage. But if we make the assumption of the classic fault where we have the flower type structure at the surface, we include the borders damage, and as you go deeper and deeper down, this becomes more and more confined. Maybe we can make the assumption at greater depth where we have most of the seismicity that we do just have a narrow interface. Maybe we can make that assumption. I'm not sure. You know, the jury is out on that.
Yeah.
But yeah, great point. Great point.
Yeah,
I'll definitely keep you up to date about how that's going, for sure.
Sounds good. Just a quick comment that at least near the surface, in some cases, including Anza, there is evidence that these zones are couple kilometers wide.
Absolutely.
They may be getting narrower with depths. We do not know that yet. I think more work is needed to actually resolve what is happening to these zones at depths. But one of the questions there is actually what happens, for example, if we don't have a really nicely localized slip interface, and it can happen on one side of this damage zone, on the other side of this damage zone. Possibly this would switch the polarity and the preferred rupture direction. So Absolutely. Just something to think about. My other question was about the MT, and the question is, my understanding is that the EM signature of a fault zone or a damage zone would depend on at least three factors. One is the fault zone width, the other is the porosity, and the third is the salinity of the fluid, right?
And interconnectivity, and that kind of relates to porosity, yes. but yeah, it needs to be connected, yeah.
Yes, the topology of the porous space.
Yeah.
So you probably done the sensitivity calculations, and my question is how large these parameters need to be. In other words, how big the fault zone needs to be, and how well saturated it needs to be when it gets picked by, when it creates an anomaly in the EM data.
Yeah, and a great point. And that kind of comes to what's happening, you know, if this fault is northeast dipping in the mid-crust, you know, might we not be seeing it? That is definitely a possibility. I'm not discarding that at all. Yes, I did do the sensitivity tests. I mean, you can see on this plot over here, within this 3 kilometer wide fault zone, we have about 10 to 12 empty stations. So this feature, this steeply northeast dipping feature, is the best resolved feature in this model space, because we're near the surface. Mostly higher frequencies with high resolution are sensitive to it. And we also have the most stations because we knew the fault was there at the surface. So this feature, C1 especially, is the best resolved feature in this model space. And then, as you say, as we go deeper and deeper down, you start losing resolution a little bit, slowly but surely. But yeah, I mean, just to your question, for example, this feature C1, it's incredibly well resolved. I also did synthetic tests where if you go to greater depth, C2, for example, I try to move C2 towards the northeast, and I try to move C3 towards the southwest. And the results also showed that R1, so C1 and R1 are both very, very well resolved. So if the San Andreas fault in this area is cutting through R1, then it must just be, you know, either super dry and undamaged, or the cracks and the fluids must be at such a scale that we just can't see them. So that is a possibility. I'm not discarding that. But C1 for sure is very well resolved, yeah. And
so what is your interpretation of these deeper anomalies? Because I think the consensus seems to be that the pore space decreases with depth, right? So pores tend to close, and so the fluid content goes down. And what can create these large anomalies below 15 kilometers? I'm curious.
Yeah, so firstly, you need super close to saline fluid. So you need fluid that's very salty, almost like seawater. And then you just need that fluid to be interconnected over very large distances because the wavelengths at this depth are long themselves. So it needs to occur over a large distance. But that's what we have at a transform fault, right? We've had ductile motion for many, many, many years. You've got shearing, shearing, shearing. And so, you know, we don't see them just here, but we see them along other active transform faults as well. So very, very minute amounts. I'm talking about less than 1% of saline fluid interconnected over many kilometers will cause those type anomalies at lower crustal depths.
Well, 1% porosity is pretty big.
Less, but much less. I think it's like 0.1 even. It's very, very, very small. It's really small. I can send you the latest draft of the paper. I can't remember the number right now, but it's well below 1. Yeah.
Okay. Thank you.
Thanks, Yuri.
Peter.
Yeah.
Peter, sure. I mean, I still have a question, Peter? You're muted still, Peter.
Mhm.
There you
Okay, yeah, sorry. Thanks for the talk. It was a nice summary of a lot of material. I wanted to ask about the tomography model and one of the plots you had at depth. I think it was about 19 kilometers, something like that. Yeah, it showed that feature where you I don't know if I can draw on there. That slow diagonal feature there. How sure are you that that's resolved? Because it looks, I mean, I see as I'm sure you know, you can get these kind of artifacts if you have if you were, for example, to have a lot of the ray paths, you know, that would go right along there.
Yeah.
Do you have a lot of rays through there that go at various angles? Because I'm just a little worried about how the resolution, you know, at that depth, that you'd be able to see something that narrow.
Yeah, no, thanks, Peter. That's a good point. That's always a very valid concern. So firstly, yeah, when we select the data, so you're right. Like right after the El Mayor event occurred, there was a rapid deployment of seismometers right on top of the rupture area. So we do have more seismic stations right on top of that feature than we do in the surroundings, especially in northern Baja. But in the data selection process, I do select data. I don't include all the data. I try and select a data set that's uniform, both in terms of distances, epicentral distances, and in terms of the azimuthal ray coverage that we get from them. And then obviously, once I have my data set together, we go through all the sensitivity tests. And so as far as I can tell, yes, we do have many rays, but it's not simply a case of all my rays are orientated, you know, parallel to this feature right now. They are crisscrossing from all directions. And this feature is also, you know, pretty close to the center of the model space. So there's a good chance that would be the case, right? And yeah, so I've selected the data in a way that creates as much uniformity as I can. And the synthetic tests just show that, yes, it is well resolved. And so I'm sticking on it for now until somebody, you know, proves me otherwise, as happens in science very often. Yeah.
Okay, thank you.
Thanks, Peter.
Hello, this is George. Can I get a question in? I don't know if you can hear me.
Absolutely.
Yeah.
Go ahead.
Yeah, I'll follow with Yuri's example. I'll ask a seismic one and then an MT one. The seismic one is pretty simple. In a sense, have we seen the end of the San Andreas extension there, just east of the Salton Sea? Is it now just normal crust going in the strike direction further to the south?
Yeah.
So that's the one. That's, you know, it looks like it's stepped over completely. The way I see it, steps over to the other side, meaning to the west of the Salton Sea. The MT one, you guys got to get the funding. That's for sure. For 3D, you need more data for sure.
Absolutely.
But I'm very impressed with what you have already shown there. And I think an opportunity to look at some of those data, especially when you get additional profiles, and compare with focal mechanisms from earthquakes in the area would be very, very interesting. And to assure you, in New Zealand, we definitely have less than 1% water as long as we have dihedral angle wetting along grain boundaries. We'll have a conductor that's detectable at depths. You're talking about tens of kilometers, et cetera. So
Yeah.
those are my questions, comments.
Yeah, I'm also very curious. Oh, sorry. I'm also very curious about the extension of the San Andreas. You know, it's just kind of, it's a line on a map now and the line ends, but I'm pretty sure something's happening for the southeast. And that's why you can see we are trying to at least have some of those profiles cross that section, that exact section of the San Andreas. And so I'm showing you in the proposal, I mean, we've got a phase 1, but if we see some sharp contrast in exactly that location that you just specified, we'll fill that in with a couple of more stations, just to make sure that we're quantifying that change too. Yeah, and about your focal mechanisms, I mean, you know, that is the problem here. You know, we are not blessed with seismicity along this fault. So we can do some of that, but we are limited. And yeah, I agree. I mean, this is long overdue. We should get more empty data collected in this area and just tie all of that in with all the other geophysics, because it's a perfect opportunity. I mean, we've got a sedimentary basin. We love installing empty stations and sediments because the digging is easy. And, you know, we don't have a lot of seismicity. So seismology sometimes is a bit limited. And the sediments also challenges some of the geodetic tools because you don't have the hard rock benchmarks that you can use to get some good quality data from. And so empty to me is just a perfect complement to all of those tools. And I hope for some good news too, but as all of you know, I mean, you know, funding comes and goes, and sometimes you get lucky and sometimes you don't.
Peter, let me ask you, I thought EarthScope was going to end up going down to the Salton Sea area.
They did. So these green triangles that you see, and if it's clear. So we do have some data. So Adam Schultz and his team have collected that data. And those are, but as you can see, it's on a very different separation and scale than what
Absolutely.
Yeah, those are about 70, 60 kilometers apart, you know, ring stations. So we have that data and we can use that, but we really need some high resolution stuff to figure out the plate boundary better.
Well, very, very high marks, and congratulations on your professorship and also joining SAGE.
Thanks, George. That was great seeing you, and I'm sure we'll be in touch in some way or form.
Great, good, absolutely.
Well, we are several minutes over the canonical hour.
Yeah, people can just email me, Dan, if they want. I do not mind.
Yeah, absolutely. This conversation can continue if you would like. Reach out to Peter individually, and he's, I'm sure, more than happy to collaborate and work with all of you. But to respect people's time, we'll sort of close the seminar officially here. And so we want to thank Peter once more for an amazing talk, and we'll see you next week, next Tuesday, for the next seminar. Thank you very much.
Thanks, everyone, and happy 2022. Yeah, let's hope for a better one. Bye, Dan.